All right, section 6.2. We're going to be looking today at what are called inverse functions. We're going to take a look at how to tell graphically whether two functions are inverses of each other, or sort of what a characteristic is that two inverse graphs have in common with each other. And then we're going to take a look at how, if you're given an equation, how to construct the inverse equation from the one that you're given. And so let's first just talk sort of what an inverse function is, or an inverse relation is. The key defining factor of two inverse relations is that the domain of one of the functions is actually the range of the other, and vice versa. So this takes us back to the beginning of the year. Remember, domain, those are all the x's, all the x values, and range, those are all the y values. So let me just give you an example here. Let's say that we let these 3 points here, we'll just call them relation A. These are relation A, and then over here, these 3 points are relation B, and these are inverses of each other. And so what you'll notice is you will notice that everything that was the domain in relation A has become the range in relation B, and everything that was the range in relation A has flip-flopped and become the domain in relation B. And so essentially what happens when you're wanting to create the inverse is you just flip-flop the x and y. So instead of the point 1, 5, you can see over here for relation B that has become the point 5, 1. And then 2, 6 becomes the point 6, 2, etc. Okay? So it says here, for an inverse, the domain values of the original become the range values of the inverse. Likewise, the range values of the original become the domain values of the inverse. And so when you do this, when you flip-flop the x and the y values, something very unique happens on the graph. And so I want to explore this with you just with this first example here. It mentions that the vertices of triangle ABC can be represented by the relation, and then they give you these 3 points here. So I'm going to go ahead and plot those 3 points, and I'm going to label them A, B, and C here. So at the point 1, negative 2, we're going to call that point A. At 2, 5, right here, we're going to call that point B. And then 4, negative 1, that will be point C. Oops, I plotted that wrong. Sorry. Positive 4. Negative 1. That would be right here. Okay, so we're just going to connect those dots together here to get our triangle ABC. Okay, now the question is, find the inverse of this relation. Okay, so they want us to find the inverse to triangle ABC, and then they want us to describe how that graph might relate to the original graph here. Okay, well, if we're going to find the inverse, I'm just going to label inverse here. There is a special symbol that we're going to learn here for how to label an inverse, but for right now, I'm just going to list what our points are. So for the inverse to point A, okay, I'm just going to give it a little apostrophe here to show this is the inverse. I'm going to flip-flop the x and the y values. So instead of the point 1, negative 2, you can see I flip-flopped them. That'll be the point negative 2, 1. This B with a little apostrophe, I'm going to flip-flop the coordinates for B, and then the same thing for C. Now I'm going to plot these new points. I'll switch colors so this will be a little bit easier here. And we want to label them A apostrophe, so we know that that's the inverse point. We want to do 5, 2, it's the inverse for B, and then negative 1, 4 would be the inverse for C. Okay, and we're going to connect those so that we can get that triangle. Okay, now it is a little bit hard to tell if I asked you to look at this graph and kind of tell sort of what the connection is that you're seeing between how the original triangle ABC relates to the inverse triangle A apostrophe B apostrophe C apostrophe. And so to help you sort of see that connection, what I'm going to have us do is I'm going to have us draw in the graph for the line y equals x. Okay, and so to do this, we're just going to pick some points for x to go ahead and substitute into the equation here so we can get a corresponding y value. So let's go ahead and we'll just plug in -1, 0, 1, and 2. Of course, if you substitute a -1 in for the x, what you're going to get back out for the y is also -1. 0 going in for the x, you basically get the same thing back out because the equation is simply y equals x. Okay, so let's go ahead and see if we can plot these 4 points here. Okay, and this is going to construct a line that we are going to go ahead and sketch here. I didn't do a great job of drawing that here. I'll just try to maybe thicken it up a little bit here. Okay, so I want you to look at this black line. That is the line y equals x. There's a specific reason that I chose to graph the line y equals x. It also has a distinct connection between an original graph and its inverse. But I want to see if that in any way helps you see the connection between the red triangle, the original triangle, and the blue triangle here. Okay. Now again, it is a little bit hard to see, but if any of you are noticing, if you were to use the line y equals x as a line of symmetry, imagine that you were going to fold everything on this side of the line over against this side of the line here. It would kind of feel like this red part of the triangle that's up here might land right on top of the blue part of the triangle here. And everything that's on the red part of the triangle down here, if we were to fold on the black line, it would land directly on top of this part here. So it feels like the original graph is being reflected across the line y equals x, and the reflection is the inverse graph. Okay, and that's what we're going to fill in on, and you can see I did this bottom one for you. You can kind of see that represented down here again. I have this dotted green line as being the line y equals x. And again, a little hard to see, but they are reflections of each other. And so if we want to describe how the graph of the inverse looks, we could say something like this. The inverse graph the inverse graph is the original graph, reflected over the line y equals x. Okay, so we're talking about the original graph is reflected over the line y equals x there. Okay. All right, so on the next page here, we're going to fill in just a couple blanks. It says the graph of an original relation and the graph of its inverse is what we just filled in earlier here, are reflections of each other. Very important. They are reflections of each other across the line, y equals x. Okay, across the line y equals x. And we call that line y equals x, that is called the identity function. Okay, that is the identity function. Now, we'll play into that a little bit more here in just a few minutes, but I want to introduce you to the symbol that we use to label an inverse function or an inverse equation. Okay, the symbol, instead of f of x, the symbol has a little -1 kind of squeezed in between the f and the x. When you see that symbol, it does not mean to move this f to the denominator like we learned about negative exponents. This is merely a symbol. This is all glued together as one thing, and that symbol represents the inverse of your function. Okay? Now, we learned this early on about functions all the way back in chapter 2. We learned that if your x values repeat themselves, then your relation is not a function. Okay? That would be like the original would not be a function. But I want you to think about this for a moment. If you're looking at an original graph and you can tell, okay, the x values don't repeat, so that's good. That means that that original graph is a function. But what if the y values of the original graph repeat? Okay. If the y values repeat, the original graph is a function, but what we would be able to conclude is that the inverse won't end up being a function. And here's the reason. Remember, to create the inverse, the x and y values get swapped. So if the original function has y values that are repeating, those repeating y values are going to become repeating x values in the inverse, therefore deeming the inverse not a function. And so we have these two tests. I know that we learned this first test in chapter 2, and that was the vertical line test, but you should only use the vertical line test if you are actually looking at the graph that you're asked, is this graph that you are looking at in front of you a function? Okay, the vertical line test basically tests for repeating x values. Okay, so if you're asked, hey, is this graph a function? Then just apply the vertical line test. However, if you're given a graph and you're not asked, is this graph that you're looking at a function, but you want to figure out if you changed that graph into its inverse, would the inverse be a function? Okay, keep in mind, this is assuming that you don't actually have the inverse graph to look at. You only have the original graph to look at. Then you should apply the horizontal line test, because this will test for repeating y values. And it's those repeating y values that become repeating x values in your inverse. Okay, so let's try this. You can see that we have a couple of graphs down here. Okay, I don't think this red dotted line is supposed to be here initially. Now, you're being asked two questions. You're being asked, are the following graphs functions? So these two blue graphs that you see here, if you're asked, is that graph a function? We're assuming these are the original graphs, not the inverses. You would apply the vertical line test. So the question is there any place on either of these graphs that you could draw a vertical line and it would pass through the graph in more than one point? And it looks like in both of these graphs that they both pass the vertical line test. So where it says just f of x or g of x, I'm going to say that yes, both of these graphs are functions because they pass the vertical line test. Now, if I'm asked, would the inverse to these graphs be a function? Now, I don't want to do the vertical line test. I want to apply the horizontal line test because I'm wanting to check for repeating y values. Okay, so now I'm going to use my notation here for the inverse. This should be a little negative 1 here on each of these. Okay, so you would say to yourself, well, can I draw any horizontal lines that would pass through these graphs in more than one point? Well, on the first graph, it feels like that would pass the horizontal line test, which means I could conclude, even though I don't know what the inverse graph looks like necessarily, I could still say that I know that it's going to be a function because the original graph passes the vertical line test. You can see this dotted red line that's drawn here is an example of this not passing the horizontal line test. That actually crosses the graph in 4 places, which means that in that location, there are 4 repeating y values. Those 4 repeating y values will become repeating x values if we were to switch this into the inverse graph. So we're going to say no way would this graph end up being a function if we switched it into its inverse. Okay, so you got to watch how the question is worded, whether you're applying the vertical or the horizontal line test. Okay. All right, so what we're going to look here in this next section is we're going to switch over to equations. Okay, you'll notice we are not given graphs at all. Here we are given simply an equation, and the question is asking us to find the inverse for each function. Okay, now it does mention to graph it on your calculator. We're just going to create the inverse equation here. Now, there are 4 steps in this box that you'll want to follow when we're going through this process. So please reference these 4 steps here. Okay, what we're going to do first, step 1, it says you're going to replace the f of x symbol with a y. Okay, it's just going to make this a little bit easier if we have x's and y's instead of f of x's instead of x's and f of x's. Okay. All right, so we've replaced the original symbol with a y. Now, the next thing we're going to do, as we do when we create inverses, is we should swap and exchange the x and y in the equation. So the only thing that you're going to swap out is you're going to trade places with just the letters. The numbers stay exactly where they're at. So you can see instead of y equals 2x minus 5, I've written x equals 2y minus 5. Okay, now we are to step 3. Now they want us to resolve this equation so the y is back by itself again. Okay, so I'm going to move this 5 to the other side. I'll add 5 there. And then we're going to divide both sides by 2 so that the y is by itself. Our final step is to now take the y out of the equation and replace it, not with the f of x symbol. We want to replace it with this inverse notation symbol, f negative 1 of x. Okay, so if we were to do that, I like to kind of put my symbol on the left side of the equation here. I'm just going to rewrite this on different sides. Here would be the inverse equation. Now, if we took the time to graph this original equation in y1 and this inverse equation in y2, we would notice that the two graphs would look like they're reflections of each other across the line y equals x. Okay. All right, let's try one more of these. We're going to take a look at finding the inverse equation to example C. Okay, step number 1 is to replace the f of x symbol with a y, and step number 2 is to swap out the x and the y so that those have traded places with each other. Okay, once they've traded places, we're at step 3 where we're going to now resolve the equation for a y. So I'm going to get rid of this 5 first from the right. That means I've got to put it over there on the left as well. And then I'm going to get rid of the 3 by adding the 3 over to the left side. Now the y's by itself. My final step is to replace the y with the inverse notation symbol, f negative 1 of x. This would be my inverse equation. Again, if we graph the original and the inverse, they would both look like they are reflections of each other across the line y equals x. Okay, we're going to end today with this test. Okay, here's our test. If you're given two functions, we will call one f, we will call the other one g. Okay, the two functions are inverses of one another if you can show both of these things. Okay, this is tying in what we learned in section 6.1 with composition. You have to show both that when you compose function f of function g, you get an x, and when you compose g of f, you also get an x. Okay, now the significance in x is that represents the line y equals x that the two graphs are reflected across. We call that the identity function. Okay, so these problems can be a little bit involved. You always want to create two columns to your work. I like to label at the top of one column f composed of g, and I want to show that that equals x. And then at the top of the other column, I want to do it the other way, g composed of f, and I also want to show that that equals x as well. Okay, now a little bit of review when we did composition. Remember, your first step is to kind of smash everything together here on the left side. Okay, again, the goal is we want to show that our answer on both columns here is going to come out to be x. Okay, remember composition works from right to left. So you're going to start on the inside here, on the right, g of x. You're going to come up to the directions, you're going to grab g of x, and you're going to replace the symbol g of x with a 1/3 x minus 3. Okay, remember, right to left. So everything that's on the right here, this 1/3 x minus 3, is going to get plugged into equation f right where that x is. Okay, so I'm going to write out equation f. I'm going to put, though, parentheses right here where that x is. I'm putting a big set of parentheses. Inside those parentheses, I am substituting a 1/3 x minus 3. Now, here's what should happen if these are inverses of each other. When I simplify all of this, it should all simplify down to just an x. Let's see if that works out this way. I'm distributing a 3. Okay, 3 times 1/3 will reduce to a 1, so I have 1x there, minus 9, and then I have this extra plus 9 that cancel each other out. Ooh, I can check that that column works good. Okay, now, you have to make sure that you do this for both columns. You can't just do one and then say, oh, well, that one worked out, so I'm good then. Okay, you have to make sure that both columns, when both compositions come out to be x. So now I'm going to do all this smashed together, g of f of x. Again, I'm going to start on the right. I'm going to replace the symbol f of x with what f of x equals, which is 3x plus 9. Okay, remember this works from right to left. Now you're taking a 3x plus 9 and you're substituting it into equation g for this x right here. So you want to write out equation g, put parentheses right here where this x is, that's what this represents, and inside those parentheses you are substituting a 3x plus 9. Okay, we're now going to simplify and see if this also comes out to be x. 1/3 times 3x is x. 1/3 times 9 is 3. Then we have this minus 3. Aha! So this also comes out to be x. So my conclusion is they are inverses of each other. Okay, what I don't want you to do is I don't want you to take one of the equations and simply do this 4-step process to see if you get the other equation. I understand that that is a logical way to go about doing this, but you need to be comfortable with knowing that when two functions are inverses of one another, this characteristic is true. So I want you to create 2 columns of work and go through each of these 2 compositions. Okay, so we're going to try one more, a little bit faster here. We're going to do composition one way, showing hopefully that'll come out to be x, and then the other way. Now, I should tell you this. If you do the first column and the first column does not come out to be an x, then you do not need to mess with doing the other column, okay? Because that's enough proof to show that they're not going to be inverses of each other. Both columns have to come out to be that x. Okay, so let's go ahead and try this left side here. Okay, we're going to smash everything together, f of g of x. We're going to replace this g of x symbol with the equation for g of x, which is this 1/3 x minus 3. Okay, I'm working from right to left, so I'm going to be substituting a 1/3 x minus 3 into this equation here, equation f, for its x. So I want to write out 3 parenthesis plus 9, and I'm going to substitute a 1/3 x. Oh, I'm sorry. I'm doing the wrong problem here. Oh, you guys are probably like, what in the world is she doing here? We got 2 different equations over here. We switched problems. Here's f and here's g. I apologize. Okay, so let's go back to this. We're swapping out the notation g of x for what g of x equals. That's this 2 square root of x, okay? All right, so I'm going to be plugging a 2 square root of x into equation f for this x right here, okay, that x. So I want to write 4 parenthesis squared, and then I'm plugging in 2 square root of x. Now, you're allowed to distribute this exponent because there's no addition or subtraction. So I'm going to square the 2, and I'm going to square the x squared. Okay, now let's think about this here. I've got my 4. If I square a 2, that's another 4. If you square a square root of x, that means you're taking a square root of x times a square root of x. What you're basically going to get is you're going to get just an x. Okay, so what I have here is I have a 16x. It doesn't feel like that came out to just be a 1x, which is what I need, a 1x. So I'm going to say not inverses. Okay, not inverses because my first column didn't come out to be an x. I don't even need to waste time figuring out my second column there. Okay, I think that you're going to find on the worksheet tonight, every single problem, you can find one example on this notes page in this video that is very, very similar to what those problems are asking you to do. So if you need to rewind, go back, watch any parts of this to help you, please feel free. The homework assignment is worksheet 6.0.